engineer at Google, and today I'm going to talk about using BPF or eBPF to customize the out-of-memory handling. So in some ways, my talk will be similar to the previous one, but applicable to memory management instead of the scheduler. My talk is the last one today, so I guess everybody is a bit tired, so I'll try to be a little bit less technical and start with a story. But before jumping into the story, I actually have a warning for you, especially for those of you who are maybe like kind of junior kernel engineers. So if you tend to open a memory OOM kill.c source file, you might see this like nice and warm and welcoming comment, which I think is like 25 years old. My friend advised, don't trust it, it's a trap. I learned it the hard way, and you will see why. So apparently OOM killers are not that simple. So let's go to the story. So back in 2017, I joined Facebook kernel team, and as some sort of an onboarding task, I got this project to make the OOM killer cgroup aware. The idea was pretty simple, like if we use memory cgroups as the main vehicle for physical memory accounting and control, why not make the OOM killer operate in terms of memory cgroups? And like maybe roughly, we can, in case of memory shortage, we can like, instead of picking the biggest process, we can pick the biggest memory group and kill it all together, or maybe it's the biggest process there. So it looked pretty simple and straightforward from the technical perspective, so I made the first versions, and upstream got some feedback, addressed it, and the second version got some more feedback. Somewhere around version 12, it became clear that like it's really hard to find a shared ground between like 5 or 6 people who were involved in these discussions. We could agree pretty much on every question with some people, but there was absolutely no way to find an agreement on all the questions between all the people. So what were these questions? So the first one, and maybe the most important one, was like, when we're picking the biggest cgroup, like should we pick the biggest live cgroups, or we should like traverse the cgroup tree and pick the biggest cgroup on each level? Each approach has some pros and cons, and like you can say that like if we're picking the biggest live cgroup, it's the closest approximation of the existing OOM killer policy, but someone else might say that this way a container can like, you know, create a bunch of sub-cgroups and spread it over like multiple cgroups, and this way avoid being OOM killed. But there were other processes, other questions like how to handle processes in the root memory cgroup, for example. Like root memory cgroup is by design very special processes in the root memory cgroup bypassing memory counting. And they also kind of don't represent a single entity. So it means we can obviously fully ignore them from the OOM killer perspective, but because they still can leak memory. So it means we somehow need to compare processes with cgroups, which is already kind of not obvious how to do it properly. And to make things worse, there is a per process interface called OOM score adjustment, which works as some sort of multiplicator for the size of the process. So now you need to compare like kind of not completely fair process size with cgroup size. And again, all this question is not that hard to kind of give some answer, but it's very hard to argue that any given answer is really the best one. Like it really depends on your workload and your configuration and your preferences. So this project got stuck at that moment. But a few months later, Johannes Weiner, he developed this thing called PSI, which is pressure stall information. It's a new set of, I would say, system efficiency, or even better to say system inefficiency metrics, right? So this metrics basically say you why, like, what's the percentage of overall system capacity is being lost because you don't have enough memory or enough I/O bandwidth or enough CPU cores. So how it's connected to the handling the out-of-memory conditions. So PSI, I think it was first time in the history when PSI allowed to reliably detect thrashing. So thrashing is a state of the system when, technically speaking, the system is making forward progress, but almost all compute resources are spent for just throwing away memory pages and rereading them from disk very soon. So this was a well-known and kind of very long weakness of the in-kernel OOM killer, because it just can't reliably detect this condition. So PSI allowed to solve this problem. So how you basically, like in a user space program, can poll PSI values. PSI works somewhat similar to load average, so it just shows you exponentially decaying averages for, if I recall, 10 seconds, 1 minute, and 5 minutes. And at some point, a user space program can decide that enough is enough, and it's time to do something more drastic and maybe kill some processes. And this is exactly what was implemented and got the name OOMD. So OOMD is a user space OOM killer. So I think it evolved from a very simple version, which was basically a bash script, to something very complicated with detectors, actions, plugins, very complicated configuration system. But the basic idea was the same. It polls PSI values at certain predefined threshold values. It killed some processes. What's important that the user space OOM killer was never meant to fully replace the in-kernel OOM killer. It's just not as reliable. So the idea was to use two OOM killers, and a user space OOM killer should be some sort of a front end for the kernel OOM killer. So it means that in majority of use cases, the hope was that user space killer will kick in first and do something nice, smart, and gentle. And if it fails to do so, we still have the in-kernel OOM killer to unblock the system from being deadlocked on the memory. But actually, I mean, it works pretty nicely in practice, and I think to these days, many big systems are relying on this. But because you have two separate OOM killers, and they are completely separate. They don't have nothing in common. They don't know anything about each other. They have completely different logging pipeline, statistics pipeline, and they can actually race against each other. I think handling this two OOM killers by any sort of cluster management system becomes more complicated. And also writing the OOM killer in a way that it can be reliably working under very heavy memory pressure is challenging, right? So it should not allocate any memory. If it tries to read any information from, I don't know, procfs or sysfs, it requires to grab some logs, and logs can be very contended if you're under heavy memory pressure. So it's not easy, but it's doable. And later on, systemd implemented its own version, which is called systemd OOMD, and it's now a part of systemd. A few months later, I was actually kind of frustrated with my MEMC group where OOM killer being stuck, and I managed to find some subpart of it, which was less controversial. And it became, it calls memory OOM group. So one of the problems with the OOM killer was that if you have several containers running on your host, and then system-wide OOM killers kicks in and kills some random process, many workloads are just not prepared for it, and they don't know how to handle it properly. So a host can be left in an inconsistent state after the OOM kill. So it's very simple functionality was added to memory cgroups, which is called memory OOM.group, and it means that if OOM killer kills a single process, it also should kill all other processes in the cgroup. And this part was like not controversial enough to be landed upstream, and it's now adopted by systemd and other things. So now we're making like a big jump forward into 2023, so it's like 5 years jump. And in 2023, an engineer from ByteDance, Chui Zhou, suggested to use BPF for picking the OOM victim. So the idea was kind of cool, but created a lot of uneasy feelings across the MM community. But I think after some discussions, people realized that it's cool. And there is, by the way, nice LWN article describing it in details. But the implementation was very closely tied to existing in-kernel OOM killers. So basically what it does, it adds a new BPF hook, which is executed for every process in the system in case of a system-wide OOM. So when the OOM killer is trying to pick a victim task, it iterates over each task and tries to find the biggest one. And then for every task before evaluating its size, the BPF hook is executed and it can redefine the order of tasks, basically. So technically speaking, you can implement a lot of interesting things using this approach, but it feels somewhat inefficient and also feels like a BPF from like, I don't know, 5 or 7 years ago, not like the modern BPF. So the feedback from several folks was, including myself, that like, hey, it's kind of cool, but like, can we do something more generic with BPF? Can we just run a single BPF program and ask it to just release some memory, right? And like, we don't have to attach so closely to existing implementation. So Chui actually looked like got this feedback very well and started working on some fundamental parts of BPF which are required for this project. It's OpenC group and task iterators, and they were landed upstream, but I don't know, for some reason this project stopped, so there were like no progress made over like 2024. And in 2025, I actually picked this project myself because I started working at Google, and like an open small secret, Google has a lot of downstream code in this place, and I was interested in like upstreaming it or dropping it or replacing it with something less invasive. And BPF looked like a really good idea here. So basically what we want from a BPF solution in this space, there are two separate parts or two separate questions. Like the first question is like when the OOM killer should kick in, or like more like what are conditions which should be met for the OOM out-of-memory state to be declared. And as I just talked, like the in-kernel OOM killer is usually too late. So we won't probably use PSI here, or like we need something smarter. And the second question is, what's the best way to free memory? Like, which might be which process to kill, but we might have some other options as well. So my proposal consists of two actually quite separate parts. One is called BPF PSI, and the other one is called BPFOOM. And they can be used completely separate, and actually BPF PSI can be useful outside of out-of-memory handling. So let's look at these two parts. Okay, so both parts are now implemented as BPF struct ops, which is the most generic and powerful way to implement complex things in BPF, and like scadext is also implemented using struct ops. So BPF PSI has just, as of now, it has only 3 simple callbacks. The first callback is called init. It's just called every time the struct ops is loaded into the kernel. The second callback is called handle PSI event, and as you can imagine, it calls every time a PSI trigger is fired. Yeah, I forgot to say, like, as you can imagine, polling events, polling some values from a BPF program is not very handy. So in order to use PSI from BPF, luckily we have a thing called PSI triggers. So it's basically a way for a user space program to predefine some window and threshold value so that the kernel will send an event to a user space program when this threshold is reached. And now you can, oh, sorry. Yeah, I didn't touch anything. Okay, sorry. So yeah, we have PSI, handle PSI event callback, which will be called every time a PSI trigger is fired. And we have a callback which will be called if a corresponding C group is deleted. So let's look into an example of a BPF program which implements a custom PSI trigger. So the init callback is very simple in this case. I'm just creating two PSI triggers, one for memory PSI and one for IO PSI, and both with a threshold of, with a window of 1 second and a threshold of 100 milliseconds, and they are attached to different C groups. And obviously you can create as many triggers as you want. You can have like multiple levels for the same C group. You can like attach a trigger, separate trigger for each C group, so you can easily monitor the whole system. So what a PSI event handler can do? So in this case, it's very simple. So it basically receives a pointer to the PSI trigger structure, and from it, it gets a pointer to a memory C group. And when it gets a pointer to a memory C group, it declares it out of memory state in this particular memory C group. Let's look at this function, which is BPF out of memory, right? So this is basically a BPF kernel function which allows to declare out of memory state out of BPF. It has a pointer to a memory C group, which can be null if you want like to declare a system-wide OOM. It has a page order argument, and it has flux argument, and the flux argument has, right now it's only one flag, which means the kernel should be blocked on the OOM lock. So the tricky part here is that like for system-wide out-of-memory states, you don't really want to run several concurrent OOM killers, right? It does make sense. If you already have a OOM killer running on one CPU, it will probably free up some memory, so everybody else should just bail out. For memory, like for OOMs in memory C groups, it's not that simple, because in theory you might have two OOMs in different parts of your C group tree which are completely independent. So in case your OOM lock is contended, you probably want to wait. So let's see how it works in practice. So this is a demask output from a test program, where you can see that PSI trigger is executed from a context of a work, and this like it's painted in blue, and then it calls a BPF program, which is in green, and it actually calls into out of memory function, which is the main entry point for the kernel OOM killer. And then it calls OOM kill process, which is just normal out of memory handling. And also you see that this constraint variable is displayed correctly, so you can like make sure that like somebody can understand what happened looking at the mask logs. Okay, so that was the BPF PSI part. So now let's talk about BPFOOM part, which is the way to customize the OOM handling policy. So it's also implemented using BPF struct ops, and the interface is actually even simpler, right? So you have just really one callback and one text field, which is the policy name. And the callback is called handle out of memory, and basically its single task is to release some memory, and it doesn't matter for the kernel the way it does it, right? Like it can do anything it takes. And similar to the in-kernel OOM killer, it just gets this pointer to the OOM control structure, which describes the whole context and scope of the out-of-memory event. So let's look at the example. Sorry, it's a little bit longer, so I had to split into, I think, 3 screens or 4 screens to make it readable. So in the first part of it, we need to get a pointer to a corresponding memory C group or root memory C group when it's like a system-wide OOM. Because BPF guarantees the lifetime of like all objects which it gives access to, and like it should guarantee your memory correctness, right? In order to access to memory C groups or even to root memory C group, which is technically immortal and like shouldn't, like you don't need any additional protection and like poor kernel code. In BPF, it's not that simple, so you have to use special function helpers to get like a valid pointer to the root memory C group. In the second part, which is more interesting, we actually iterate over subtree of C groups under the memory C groups, under the memory C group, which had the out of memory event, and we are skipping all non-live C groups here, and then we get the pointer to like memory C group, and we have a full access to like memory C group statistics or events or current size. So in this kind of demo example, which is not really a production code, but in this example, like basically we get the size of the C group, and then we subtract the amount of page cache, and then if memory C group is killable, and it's like the biggest one across live C groups, we select it as a victim memory C group. And this memC group killable is actually just a helper function implemented fully in user space BPF, so like you don't have to write your kind of complicated logic of like a big single function. You can structure it easily. And what it does, it iterates over all tasks in memory C group, and if any task is unkillable from the OOM killer perspective, it marks the whole memory C group as an unkillable. And finally, when we have selected a victim memory C group, we can iterate over all tasks, and if they were not previously selected as OOM victims, we can kill them using the BPFOOM kill process helper. And what's important here is that like this helper will work exactly as the kernel OOM killer does. So it will use OOM Reaper, it will give the victim task an access to some extra memory reserves. So it will behave differently to what like user space OOM killers do. And hopefully more reliable, right? Like the kernel OOM killer has a lot of tricks and features to work reliably under heavy memory pressure, and now it's all available from a BPF. So this BPFOOM kill process helper is actually very simple. It just takes a pointer to the OOM control structure. It's and a task to kill and some message to print in the mask. So an important note here is that if I go back to the interface of BPFOOM ops, this handle out of memory callback, it returns an int value. And the idea here is that like if it returns 0, the kernel fallbacks to the default OOM killer. It just means that like it didn't manage to free up some memory. And if it returns 1, in theory the kernel is free to bypass the actual OOM killer and just return. But because BPF in general promises to be safe, there is an additional protection mechanism built in here so that if somebody loads just a BPFOOM handler, which always returns 1 without doing anything, I implemented like additional safety mechanisms so that basically there is a special flag in this struct OOM control structure, which is not accessible for writing directly from BPF, but when BPFOOM kill process is called, it actually can set it if like some process was killed correctly. So it means that if basically to bypass the actual OOM killer, BPF should return 1 and kill some process. And obviously later we can add some new features like, I don't know, deleted TMPFS file or like, you know, do something else. Cool. Let's see how it works in practice. So again, like demask output from a test program. In this case, you see that that was actually a normal memory C group OOM, like painted in blue, and then it leads to a calling of a BPF program painted in green, and then you can see some iteration over memory C groups and BPFOOM kill process being called, and it actually calls a normal OOM kill process function, which is used by the OOM killer to kill processes. And also you can see that we have OOM policy name printed, so you can kind of understand that it wasn't like a normal policy, it was handled in BPF. And also we have a proper constraint and a text from a BPFOOM kill function argument. Cool. So what's the current status of this project and what's next? So I'm currently at V1. I sent an earlier RFC version like several months ago. It was much simpler. It didn't use struct ops. Now I'm at V1, which was sent like, I don't know, months ago. And I'm about to send V2 with, when I address a couple of questions here. So what are these questions? First, we need to additionally restrict some kernel functions because they are not safe to be used outside of BPFOOM or BPF-PSI context. For example, if we allow to declare out of memory state from like a random place in the kernel, like we can easily deadlock on OOM lock. So we have to be careful and prevent such scenarios. The second question is a bit more tricky, and it's about like, what if someone wants to have multiple OOM handling policies in the system? With BPF-PSI, it's simple because like you can load as many BPF-PSI programs as you want. They kind of work completely independent, like so there is no problem with having, I don't know, hundreds of them on the system. It's not a problem at all. But with BPFOOM, it's more complicated because like if you have 5 different OOM handlers, it obviously does make sense to call all of them one by one. Like, you know, if one manages to free up some memory, it's probably enough. But then it becomes very important in which order they are executed. And my current version is a little bit too simple here, so it just implements a single list of all loaded struct ops structures, and they are just populated and executed in natural order, and it's probably not good enough. The second problem is that like we probably want to attach them not only on the system level, but also on the container level. So containers can implement their own OOM handling policies. And this is even more tricky because like there is some elements of the policy, how exactly they should all work. But I hope to kind of address this and send V2 pretty soon. So overall, I got pretty positive feedback on this, and there are like two or three different teams who are interested in trying this both on Android, on the server side, and I guess on systemd. And some potential ideas for the future, like we probably need another hook for monitoring new C group creation, so we can like install new PSI hooks there. And another important area which I didn't touch at all is like customizing what we report or how we report information when OOM is happening. And my personal opinion here is that like maybe we want to move away from using dmask at all, but it's a big topic. That's pretty much it from me. Yeah, some kind of trying to wrap it all, I think. It's kind of amazing how far BPF went from like 2017 to now. Like it was not even close to be possible to implement something like this in 2017. There were no struct ops, there were no sleepable programs which are required to iterate over C groups and also to kill processes and like do some complex stuff. There were no open iterators. So basically in 2017 it was possible to implement only something very simple as what was their first BPFOOM proposal. And I guess it might, depending on the timeline, it might be the first or second, I guess, usage of BPF inside the memory management subsystem, but I believe there are, I believe there will be way more very soon. So there are other kind of areas which look very appealing. Yeah, cool, thank you.
Hey, thank you for the presentation. If I've been following it correctly, right now, this BPF-based OOM killer is triggered by a PCI event, right?
So there is a BPF PSI part which allows you to trigger OOM kills, but like it allows you to trigger like normal OOM kills. You don't have to use both parts, right? So there is one part which allows to use PSI to trigger OOMs, and there is the other part which allows to customizing OOM policies, and they are completely separate.
Okay, so like if there's an inline invocation of the OOM killer, you can still use the BPF programs to select who dies.
Yeah.
Okay, thank you.
What would you say are the pros and cons between your approach and the userland OOMD?
Yeah, good question. Well, first I have to admit that like my approach is not used in production yet, so like I don't know, right? So that's the real answer. But in theory, as I said, first benefit is like you don't have two OOM killers anymore, right? Like you can implement everything in BPF, so you don't need anything else. So it simplifies the user space logic quite a lot. Second, in theory, like to my knowledge, like the user space OOM killer is not never 100% reliable, right? So you still have like both user space OOMs and like kernel OOMs, and it means like your logic works 99% of the time, but not 100, right? And BPF allows you to kind of reach kernel level reliability with all the benefits of user space solution. So it kind of combines best of two worlds, in my opinion.
Thanks.
So if I understand correctly, what you say, it means that if you attach a BPF OOM handler, it will never allocate, for example, so it won't have any issue running. It won't try to trigger allocations.
Sorry.
Is that correct? Will a BPF OOM program or BPF SI trigger allocations?
Yeah, I mean,
when you have a callback, will it need to allocate new memory to evaluate?
Yeah.
Okay.
I mean, yeah, you obviously don't want to allocate a lot of memory from like BPF OOM handler, yeah. If it, sorry.
Yeah, that was my
Okay.
question, yeah.
Do you have a BPF script which will kill more eagerly if people are clapping loudly?
No. but now it feels like a big miss, yeah.
One question. When you have a OOM, I suppose there are a few ways you want to queue the process for the C group in production. So do you expect to have different on these BPF programs, or is it going to be maybe one or two that people will just configure it?
No, I think there will be several, right? Like I think for like a normal desktop or like a phone usage, you probably want something relatively simple. But for big clusters, right? Like those things are usually integrated into your cluster management system, and the whole logic of which workloads have less value and can be killed. It's really kind of it can be determined just based on like in kernel statistics, right?
Like what type of statistics are those? Like memory allocated, or like somehow the program name? What kind of statistics do you think it will be that will require a BPF program to have a heuristic on?
I mean, it's really, the whole point of using BPF is that like you're really flexible, right? Like you have a full access to all data in the kernel. Like in my example, I was using this like helpers to access memory C group data, but it just really for convenience and for stability of API, so you don't have to kind of rewrite all your programs for every kernel version, because like we tend to change the internals of memory C group implementation quite often. But you still have the full access to all data structures in the kernel, right? So like you can implement anything you want really. And I guess we also can, like, right now it's just really one way to trigger, one new way of triggering OOM events from based on PSI, but we can add new stuff, right? Like if we want to, I don't know, use something more sophisticated in the page allocator pass, it's fairly easy to add new stuff, right? So it's really, we might have a set of triggers and like different ways of handling.
Thank you.
Thank you.